rested a little bit. I'm still sorry that I did yesterday. I thought I have a half hour more for lecturing, and that I kept you away from lunch break so much. And so I promise today I have checked the schedule and I know how long I'm supposed to talk with you. And so I promise I will be in time. I think the microphone is gone again. It's not working. It was working until 2 seconds ago. Is it okay? Yes. Okay, good. So today you have two more lectures from me, and I would like to show you a few examples in two directions. So the first topic I would like to discuss is a little bit flow chemistry, and I would like to show you a few examples how that can be used and what might be really attractive in doing this. And then the second lecture today, I would like to discuss with you a synthesis which was done in pharmaceutical industry on large scale, but it was also done in academics a lot. There are many groups have developed a synthesis towards this molecule, and I would just like to discuss with you the synthesis and then simply compare and see maybe what considerations are when you develop something in an academic lab. And so that's probably your typical situation when you do something during a master and PhD thesis. But then if you would like to apply it in industry on scale, that then maybe there are factors you need to consider which you might not consider in an academic context. So let's start a little bit about flow chemistry, right? And flow chemistry became very attractive because it has this idea that you have your reactants as a reservoir, and then you, with pumps, and you dissolve your reactants, and then with pumps you pump it into a reactor, and the reaction takes place in that reactor, and then you remove it again. And so I'm not sure how much you have heard about this before, so let me see if you are still all with me. So what do you think is an advantage and what is a disadvantage? If you would like to say, rather, I'm not doing the chemistry in a flask, I use a flow apparatus and utilize the idea that I just have a reactor where my reagents flow through, and then I can do the reaction this way. And so let's just randomly collect maybe some thoughts about this, and then we can go through a few general considerations, and then I show you actually a few real applications in chemistry. So we have a new number, or again a QR code, whatever you would like to use. And let me see, it should work. Okay. So first idea is reactions might be faster than in a flask. And reaction speed indeed is a very critical parameter where I think we still need to improve in general a lot in. Because if we look at especially many of the academic reactions which are developed in academic laboratories, we read like 12 hours of reaction time, 24 hours, 48 hours. Sometimes 12 hours reaction time just might need you go home in the evening and come back in the morning, right? Sometimes we don't know how fast the reaction is. But indeed, in many cases, a flow apparatus, a flow approach might improve yields, might improve the rate of the reaction. And indeed, one of the big issues people raise is that scalability is better, is easier, and especially one factor in the scalability, and I don't know if you ever ran a reaction in your lab, which you first do on, let's say, on a scale where you get 50 milligrams of your product, and then you do the reaction and you want to have 1 gram. And so then you might say, oh, I go now and just make the reaction 20 times bigger, right? I use 20 times more solvent, I use 20 times more reagents and more substrates. But very often you find out that the reaction doesn't work so well any longer, because there are suddenly other factors, right? The heat dissipation might be different. For example, if you have an exothermic reaction, on the small scale you don't feel it because there's little heat which is evolving, but on a large scale suddenly that might dramatically change. And then especially if you then do the next step and go to 100 gram or even to kilo or ton, essentially it means that every time you try to scale up a batch reaction, you need to do a new optimization. And that can be very tedious and in many cases might not even work. And you all probably know when you submit papers these days, reviewers will always ask at least for a gram scale. We had recently a paper where we made 15 grams. We were very proud of us. And then the one reviewer said, 15 grams, this is not scale up. You need to do this on much bigger amounts. So it's a big consideration. And the nice thing about flow is that once you have a flow system running, all you need to do for scale up is just let it run longer. But concentrations are not changing, right? Because it's in your reactor, it has the same time, it has all the same concentration, it has the same energetic characteristics. And so from a scale up point of view, flow is not only offering that you can do a scale up, can run a larger reaction simply because maybe your flash is not long enough, but very important, the optimization to scale up a reaction is much better. Less reaction time, indeed. Safety is really a very important buzzword, and I show you reactions which definitely would be more problematic in a batch setting if you would from a safety point of view. Okay. Then the disadvantages. Also, some of you write something. Potential for clogging. Absolutely. Right? You have a tube reactor. You pump your reactions through. If for some reason you should have precipitation of a salt or whatever, it might clog your system, then you might have a real problem. And so clogging is a problem. Let's see. Another problem might be gases, which might evolve, right? And I nevertheless show you a reaction today which we ran where a gas is indeed formed. But of course, if you are in a closed system, when you have suddenly gas evolution, you build up pressure, right? And so but that is something one can handle. The one or two aspects nobody wrote for you here so far is, it's probably more complicated to set it up, right? A flask, we take a flask out from our lab, just put the flask on the hood, reflux condenser, oil bath, add everything, and that's it. A flow apparatus usually is more complicated. First of all, you have to have the apparatus. You have to have pumps, which are pumping your reagents through. You need to do something about potential pressure upbuild. Very important. So you need something like a back pressure system which controls this, and when too much pressure is building up, then the flow rate needs to be reduced, and if that is to be done automatically, then you can also see it becomes more cost intensive, right? So there are a number of such issues. Of course, later, if you should work in an industrial company, very often cost considerations for equipment are much lower than everybody or some of you wrote, the reactions are faster. If you can speed up a process, and the most cost-intensive factor typically is the person who works on this, and not so much the equipment. So I have just put up some issues here, right? So typically you have a more complex setup as a negative here than just a flash. and pumps, valves, so you need a whole system, but I show you examples of this, that this might not be so complicated. Back pressure regulator. This is really important. This is this idea that if pressure builds up, then you need to have a feedback that the addition of your substrates needs to be slower in order to release the pressure, right? Extreme conditions. That is a very important thing. You can realize in a small reactor very high temperatures and very high pressures, and you expose your reactions only for a very short time. And that might be advantageous rather than heating in a batch for many hours your reagents, and then maybe you can, in the batch, you would do a lower temperature, but you speed up the reaction tremendously if you can apply high temperatures, but very often your products might not be stable to the high temperature. So high temperature, but very short residence time. This is the term people are using. The residence time is very important. Smaller reactors are possible, and you will see that this can be even nanoliters. Right? There can be really, really small reactors where you have very small, essentially a nano flask, you might say. And there also comes the safety issue into play, because if in your reactor the reaction takes place, but if the reactor is only nano or microliters or so big, then of course much less can happen, right? And so you have your starting solutions, but they are not in the moment reacting. They're only when you pump them in the reactor. But in difference, when you do it in a flask, you have everything in the flask already. And there's also, again, a cost consideration, because if you do a batch reaction, and let's say you do it on large scale, and let's say it's precious compounds, you have to add everything in your bed, in your flask, right, at the same time. And let's say something goes wrong, the electricity breaks down, so the heating goes down, or I don't know, you do a photoreaction and your lamp burns through or so. All your precious reagents are now already in your reaction flask, and they might be lost because you have an unforeseen event, right? Let's say even like your flask has a crack, or I don't know. In a batch reactor, you have your reservoir, and you commit only very small amounts at a time to the reaction. So in terms of something goes wrong, essentially only what is in your reactor is lost, but not the overall defeat you want to bring in. So this is like the lower risk of losing materials. Much better surface area to volume. This is especially important with photocatalysis. We discussed that when you shine lights into a reaction solution, that the light penetration might be only 1 millimeter into your flask. So what is the sense of having a big flask if the light is only only possible to reach the first millimeter of your compound? And so in a flow reactor, you can spread out, of course, your reaction solution, and this way essentially have a thin film or just a thin tubing, and so your light penetration might be much better. Okay, safety we discussed. We already discussed this. Typically, you can control reaction parameters better, and again, you only need to control it in a small volume in your reactor. The one thing which is pretty amazing in batch reactions is, don't know if you ever did it. So usually, how do we control temperature in a batch reaction? We have our flask, we have an oil bath, and then very often we measure the temperature in the oil bath, right? This is already the first thing which is essentially wrong, because the temperature in your oil bath is not the same like the temperature in your reaction flask. So there's already quite a big disconnect in this. Okay, so you can take an inside thermometer. That's typically the more accurate way to do it. But then if you especially have a large flask, your temperature in the middle of that flask might be different than the temperature on the sides. And we all know what we do. We stir rapidly. We try to stir this in order to have it homogenized. But again, if you're in a small reactor, it's much easier to keep your reaction parameters constant. Okay, so these are some general realization. Let me see if that works. I took, because I like this, and it's not working. I had a very nice video from the internet which shows like a, let me see if why is it not working? Because it's probably now got transferred to the computer here. Okay, let me see if I find it real quick again, because this was, what happened to the time when you could just open a browser and you would get and you would get the page. Let me see this. Let me see if I find it, because this was really nice. Oh God. Okay, let me see now. This was on YouTube, and this was done much nicer than I could do it because it was animated and everything. I wonder if I can see the URL which is behind this here. Okay, I'm afraid this would take too long now to find this back. I might add, oh no, here it is. Let's see if it works here.
Manufacturing chemical-based products is important to everyday life and plays a central role in the global economy. Combining chemicals with different properties and functions leads to
not sure I can get this louder,
like medicine, food, textiles,
it will be very
and
short.
household products. Previously, classical batch chemistry has been simple and effective when discovering new materials. But using this method to scale up chemical production can be problematic. There can be issues with waste, for example, heat management, or
what we have discussed, heat managing,
to cleaner, more
safety.
cost-effective chemical production is important.
But I wanted to show you what they show here, just as a general.
Around the world. Flow chemistry is a smarter way of making chemicals. This is how it works. Pumps deliver chemicals to a reactor.
This is the first thing. You have feed tanks, but they are not mixed yet, right? And only when you bring it in the reactor, then you commit only a small fraction of your feed. And then also very importantly, very often you can run flow reactions in sequence. You do the first reaction, and then you see here in pink, you add the second reaction to a second reactor. And even the purification very often can be done automatically. Here you have a schematic scheme, so you have your two tanks, and you then have to mix it. Very often you have a special mixer which mixes things very efficiently, and then you pump them through a tube, and this tubing system you can heat. What they do here, you can irradiate it, shine light on this, and do the chemistry there.
Because flow reactors operate continuously, making more products simply means running the operation for a longer time. Scaling up reactors is much simpler.
So here they give you two ideas. They say you can scale up either by what we discussed, letting it run the reaction longer, or use more than one reactor, use many reactors in parallel. And because the reactors are still small, this might again add to the cost, but it is also a safe way to scale things up, because again, you're not changing parameters. You use the parameters you have initially developed. Okay, so this is just as a small thing here. So let's talk about some more specific. Okay, this is not mine, right? No. Let's talk about a few more specific examples. And so the one example I showed you already, and I'm not going to discuss very much along, but we found that this rearrangement of this furfural alcohol to this hydroxycyclopentanone was a reaction which really benefited from flow, because one thing it clearly did is it reduced the side products, and the side products is something you can generate by eliminating this hydroxycyclopentanone under heat and acid conditions to the cyclopentadienone, and then it polymerizes. And the batch conditions called for heating up to 48 hours at 100 degrees. The flow conditions, we were able to do this at a much higher temperature, 240 degrees, and this way also a lot of pressure was building up in our system, but the exposure time was very, very short. So the components in the reactor were present for less than a minute, and that allowed us, and then they were out, you cool them down immediately, and this allowed us a high yield, very high purity, because we would simply suppress the side reactions. And that is a reaction which by now has attracted various chemical companies who have used our protocol, and I show you actually how we do this in a moment. But they have much more sophisticated ways to do this. So in their case, this little box here, this is their flow reactor. And again, they can pump, they can cool it, they can heat it, and then they pump the reactions and you cannot see anything. Maybe here they pump the reactions through these little, through little tubings which you have here. We did this in a much more easier or much more low budget type of way. So again, this is the idea, right? You have a stream of two compounds. You have to have a mixture, so you don't want to just bring them together. In these mixtures, you again bring them through valves and mix the components efficiently, and then the mixed components then go into a tube reactor, which is essentially just a coil, and which you need to heat, and then hopefully out comes the product. And what we did is, our flow reactor was a GC oven. That was attractive because in a GC oven, 240 degrees, you heat your reactions to this all the time, right? You would not like to do it in an oil bath. This would probably give you a lot of fumes. And so we would simply use the GC oven, and our tube reactor was an empty GC coil. That's all we needed, an empty steel coil, and we used this and we connected the HPLC pumps to it and just pumped the reagents through this. And so again, if you have still an oven, and most of the labs have such ovens, and of course have coils which are not really being used, that's very, very easy and quickly to do. There are much more sophisticated things. So rather than having such coils, steel coils, for example, here is just an apparatus people have developed. It's a spinning disc reactor. So what they do here is they have the feeds, but then they have where the reactor takes place. It's actually not in a tubing that the mixing comes, because they have a very fast spinning, rotating disc, which essentially mixes their components. And then you can see they have different ways, different inlets. They have inlets for the substrates and for the reagents. And you see N-butyl lithium, usually a compound which we of course have to handle very carefully. You can use this in flow type systems. And you see they bring it in here, and then it comes to the spinning disc, it spins, it gets mixed very efficiently, and then goes from this to this, and at some point you can also quench your reaction automatically. And so here they feed in methanol to quench the butyl lithium and ultimately get out the product. Again, more sophisticated clearly, but again, very, very efficiently. And I'm going to show you a few examples, especially on handling of N-butyl lithium, which I think are quite impressive. So let me see, I think these are my empty slides I want to show. So let's look at a few reactions, at some real type chemistry. And one of one of the types of chemistry which has been developed is being called ultra-fast organolithium chemistry. And that is something which really impressed me, especially when in the earlier days of flow chemistry. And this is the chemistry which has been developed by Professor Yoshida from Japan. And he has shown that you can do organolithium chemistry really in a spectacular way. And so look at the reaction he's doing here. And he's doing multiple steps with organolithium reagents. You see here like with N-butyllithium. And so he's starting with a bromonitro, with a bromocyanoarene. And then by adding butyl lithium, he's doing a metal halogen exchange and makes the lithiated compound. And look at this, it gets mixed. It's done at minus 40 degrees, so also low temperature in flow can be very easily realized by putting it in an appropriate cooling bath. And then look at the contact time, 0.2 seconds. That's nothing, right? If you consider that typically we run reactions at least on a half-hour scale or so, 2 seconds, the lithiated compound has been produced, and then he's trapping this lithiated compound with this component here, which has an aldehyde and a ketone. And you probably all know that an aldehyde is more reactive than a ketone, so the reaction of the lithiated compound will take place on the aldehyde. Then he is getting this coupling product. And again, look at this, look at the reaction times. 7.2 seconds. That is, again, very, very short. And then he is starting to generate a second lithiated compound in the same way like he's doing the first one in yet another reactor. And so this time you have a nitro-iodo compound, N-butyl lithium makes the lithiated compound, and then this again gets added to this compound here, where now the aryl lithium will react with the ketone and form this product, right? And so what he is doing here is he's generating two reagents and is doing two reactions, right? So in a way it's 4 steps. The overall yield 61%, that's still very decent. And the overall reaction time in the longest sequence here is less than 15 seconds, right? That is very important. That's of course only exposure time. And now if he wants to do lots of this product, he of course has to pump in more reagents. So the overall reaction time is of course longer, but the time you need in order to have your compounds exposed to your reaction conditions are only in the second range. And I show you, I have a picture in a moment of some of these reactors he's using, and they're commercially available, and they're very, very small, and they're very tiny, and so indeed that makes it not so expensive. Have a look here at this reaction conditions and the reaction. Besides the fact that we are very impressed, at least I'm very impressed, that you can do this chemistry in ultra short time, and if you would do it in a batch step by step, it would probably take much longer. But the question I would like to ask you, and this is the question I think I have here on the next one, so this is now, should be now possible to do this, and I showed you the reaction again. Would you be able to carry out, even if it takes longer, and the working time of students is essentially free, right, or more or less free, but could you even do the reaction in batch, right? What they can do here in flow, or would there be a problem in doing such a reaction step by step in batch? That would be my question here. So have a look here, and then you can answer hopefully here. If you would run that sequence in a batch setup, would that have worked? You see? I can see you're all confident with your ability, so you think, yes, I could do it. Have maybe a close look. What could be problematic to do this reaction in batch? No answers? I can see you guys are on strike. Give you a hint. Look at this first lithiated reagent which he's been making. Do you think that reagent is stable? So think how you would do it in batch. You would take your bromocyano compound and you would maybe take 10 grams of this, and then you would add 10 the equivalent of butyllithium, and you would form this, and this would take a certain time, and only then you would start adding your aldehyde. You see, the beauty here is, if you do this in the flow type reaction, it's enough, you use a tiny amount, you form this, and then you add essentially a few seconds later the next one. You don't need to wait if you do it in batch, you don't need to wait until you have made the lithiated component first and then add your aldehyde, right? So temperature variation in batch reactions is always harder to control temperature. But I think if you do it carefully, you can do it, right? You would do inside temperature measurements, you would add the butyllithium very slowly in order that you're not getting up the heat. I think that would be okay. And so if you would, for example, have made the phenyllithium from bromobenzene, I think you would have been absolutely okay. But you're making it here from para-cyano-bromobenzene. And a cyano group will react with a nucleophile, like an alkyl lithium or an aryl lithium. So you would have the problem that once you make this in batch, and it takes a certain time, that your aryl lithium compound would, with another of either of the starting material or already with the formed aryl lithium compound, the phenyllithium here, the phenylamine, would add to the cyano group. So you have a group, functional group incompatibility here. That is something we see very often in organic chemistry, and then especially in batch chemistry, that we have maybe certain functionalities in our reaction setup which are not compatible with each other. And that is the case here. So the phenyllithium would not be compatible with a cyano group. But in this flow approach, where you mix a small amount very fast for a very short time, and then bring your trapping reagent in there, that is a very good way to overcome such limitations. So that's another option, or another advantage of flow chemistry, is that functional groups which might not be compatible with each other might be okay simply because the exposure time, and then you add the next reaction, and an aldehyde is more reactive against the nucleophile than a cyano group. But you could not afford maybe to form over half an hour or so your lithiated compound. Okay, I don't know where this came from. Okay, and so the group of Yoshida has done this in many other variations. So if you look at this reaction here they're taking an alpha bromo ester, and they again do the lithiation, so they do the halogen lithium exchange on this position. And then in the next step, they're adding electrophiles. So they're generating the phenolithium here, and then they're adding something like methyl iodide. So they do the alkylation. And so I don't think I have to ask this again now, although I had prepared it. But you see, again, an example of functional groups which would not be compatible, because an L-lithium, an alkyl lithium compound, of course, is going to react with an ester group if you give it enough time to do so. So the one thing which is important to realize here, I would also like to mention, is such metal halogen exchanges, or exchanges from a second butyl lithium to a bromide. This is very fast. This is faster than the reaction with an aldehyde. So whenever you exchange halogens, this is very fast. But then if you give it time, the L-lithium, of course, will react with an ester group, right? And so again, he was able to show this here, that this is possible. So he takes the bromo compound, he takes butyl lithium, and then you see here you have these mixtures, and you see also the diameter in this mixture where you bring the two components together and where they get mixed, 250 micrometers. So we are talking really about very, very small amounts. And then the lithium-lithiated compound is formed. Residence time is overall is 2.24 seconds. And then because here now he's bringing in the electrophile, and the second mixture brings this in and is able to get the compounds. And again, a reaction which has a total residence time of 2.4 seconds. And you see, depending on the mixtures he's using, the diameters are very, 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 very small to do this. Okay, so again, can you send it? Then one thing which is also quite attractive is that you can run reactions in sequence. And here's an example of a Migishi coupling. And we said that solids, if solids form, you might get clogging. That is absolutely okay. But you can, of course, use solid reagents. And then your tubing is different. You have like a bigger column fit or so. And there, of course, you can have heterogeneous or even solid reagents in there. And here's an example which shows both, because here you have a stoichiometric reagent, zinc, so you have activated zinc powder, and so you essentially push your reactions through the zinc powder, and you're forming from the benzyl bromide here, you're forming the zinc compound. And so here the zinc is reacting as a reagent, but then here in the second step you have a heterogeneous palladium on charcoal, which is doing the cross-coupling reaction. And so that is, of course, only a catalyst. And so again, of course, the clogging is important. You need to make sure that you don't have a powder which, once it becomes wet, it will not allow you to get this through. But I think here a palladium on silica was used, which is porous. We all know that when we do a column, we can push solvents through a silica column quite well. And that also, of course, works with flow, right? And so that was an example where they showed that you can do palladium-type cross-coupling chemistry quite nicely. And I'm not sure, yes, I could probably also ask you if this is would be possible in flow or not. See here, you're generating a benzylic zinc compound, and you do this in the presence of an ester group. I don't know how much you have heard about these organic zinc compounds. One of the advantages of the organic zinc compounds is they are not as reactive as Grignards. So if you would have tried to make a Grignard reagent here, instead of using zinc, using magnesium, you could not have done it probably, because you have the ester group here and it would react. The organozinc compounds are less reactive. That's one of the big advantages of the Migishi coupling. Migishi got the Nobel Prize for developing palladium couplings with these zinc reagents. And one of the big advantages is that the zinc reagents are less nucleophilic. It's a transition metal, it's not a main group metal, they are less ionic, and so therefore this would be compatible with an ester group. So this reaction you could carry out also in batch, but of course was nicely shown here that such couplings are possible in flow as well. And so again, here is one of these Yoshida papers, and here you actually see one of these reactors, and you can see it. You can put it in a hand. It's 2 by 2 centimeters, and it's only a few millimeters high. And in fact, this is a reactor which has an inside volume of nanoliters. So it's a really small. It's a really small inlet. And let's look at the reaction which he did here. That is a paper which made it into Science. So something must be really good here. And you see already the tagline here, sub-millisecond organic synthesis. And the question is that needed in this case or not? And he chose a reaction where he is generating with phenolithium, the lithiated compound here. And once you have this lithiated compound, there's a reaction which is called freeze rearrangement. This lithiated compound would like to transfer this group here, which is shown in red, this amide group, would like to transfer this very rapidly to your lithiated compound. So essentially you can think about that the anion attacks on the carbonyl group and then throws out the phenol, which is a really good leaving group, right? And so then you would transfer the amide group into your arene, and then you could trap the resulting O lithium with an electrophile. This is actually a very decent reaction to introduce carboxylic acid functionality, so carboxylic amides, into the ortho position of a phenol. So if you can go through the halogenated compound, if you would try to do this directly, it might be more challenging. But what he did here is, if the electrophile he is using is the chloroformate here, and so he was questioning if that electrophile could compete with the rearrangement if you make the reaction time, the exposure time, really short. So you generate the organolithium compounds, and then essentially immediately you add your electrophile to this. And so he has these type of reactors, and he has, in this paper, he has a little bit different types. But the important thing is, look at this here. So he's considering the volume of the reactor, and he makes it successively smaller. So in the end, he has only a volume of less than 1 microliter. And the residence time is also getting smaller and smaller. And see what happens if you have still, compared to batch chemistry, a tiny volume, 79 microliters. And you have an exposure, a residence time that the phenolithium and these two meet, and you make the lithiated compound before you add your electrophile. He has a residence time of 628 milliseconds. You could not do this even in batch, right? Because this is calculated, of course, by the flow intake of your reagents, and then you can calculate how long they must reside in your chamber. And you see here's how it's done, right? The first compound here, this compound goes in here, the phenolithium goes in here, and then essentially the electrophile comes in here, and then at that point you have everything mixed and the reaction can be done. And so even if the residence time is as short as well under a second, right? So you have 628 milliseconds, so that's about half a second. You still get exclusively the rearranged product. You cannot compete, the electrophile cannot compete with the intramolecular cyclization. But then if you go down with everything, you go down with your volume and you go down with the residence time, you see here now we are a factor of 20 lower, then it is possible to suppress the intramolecular reaction because you're offering your electrophile at a very short time after you have generated the phenolithium, and then suddenly you change the course of the reaction completely, and you are indeed getting the electrophilic substitution, the electrophile introduced here, without that the rearrangement is taking place. Right? And that is, I think, simply shows you that you can change normal reactivity, which we are all used to when we consider reactions, by fast mixing ultra short residence times in order to do this. Okay. So again, could you set up this reaction in batch up? We just said he shows us that even in the flow reactor, if you have very short reaction times, it's not possible. And so here's one more example where I could also ask you if you could do this. So again, they're making an aryl lithium compound, and then they reacted with a acid chloride to make a ketone. And of course, the danger is that this ketone might react again with the lithiated compound, which you form here, and instead forms the alcohol. Right? And we all know that normally when we react an organolithium compound or a gradient compound with an ester, we are not forming the ketone, because the ketone is more reactive than the ester, and then we are forming the alcohol. Here they might have been a little bit better off. Here they're using an acid chloride. So if you compare reactivity, you see what you're making here. Let's go just quickly back and just write a little bit. So when you have carbonyl reactivity, we are typically in the situation that the most reactive, and I will only put up a few, so the most reactive carbonyl compounds I don't know what's wrong with this. I'm not touching anything here. So the acid chlorides, most reactive, and I will only put up the components we are considering. We are considering here aldehydes, ketones, ester. So this is typically the reactivity against nucleophiles. And so if we go and have any type of carbonyl compound, and we hit this with a nucleophile, then there are two aspects to consider. The one aspect is you get the addition product. And the question is this stable or is this not stable under the reaction conditions? If you have an aldehyde or a ketone, then your X would be a hydrogen on R. This is not a good leaving group. So that would stay, and if you quench it, it would typically give you, so if you have X equals H or alkyl, and you quench this now, your reaction with H plus, of course you get the addition product. But if you have a good leaving group here, so for example a chloride or ethoxide, then you will be forming the ketone, but the ketone is more reactive, or might be more reactive, it depends what you're using here. If you have started with an ester, then your ketone is more reactive than the ester, and it will add a second nucleophile here, and then ultimately give you the alcohol, which has added two nucleophiles. And so when you have an ester, you cannot typically prevent this because the additional intermediate you have is very unstable. This breaks down by elimination. We all know why that is, because the carbon-oxygen double bond is so much stable than a carbon-oxygen single bond. So it wants to form back. It's very rapid, but then you generate the more reactive carbonyl compound than you might have in the beginning, so it's not working. So if you have, if X equal, if you start with an ester, for X equal ester, this is inevitable. It will happen. If you have X equals acid chloride, you might be okay, right? Because you go from an acid chloride, which is more reactive, you go to the less reactive ketone. So in this case, in principle, it would be possible to add to a acid chloride, for example, an alkyl lithium compound or a Grignard compound, and end up with the ketone. From the terms of reactivity, this works. From the terms of practicality, it does not work very well because the reagent differences are relatively similar, the reactivity, and especially when you start adding your alkyl lithium compound, and that moment you generate a lot of heat at that, and so you are not at such a low temperature as you might be. So in practice it is difficult. People have reported this. Very often they use ultra low temperatures, minus 100 degrees. How do you make minus 100 degrees? Minus 78 is easy, right? How do we make minus 78? Sorry? I don't understand you. How do we make minus 78? No! Liquid nitrogen. No, liquid nitrogen we can make minus 196 if we have to. No, how do we make minus 78? You all have probably done this. Dry ice acetone. Right? This is what we do. We take a dewar beaker, we take acetone, we put in dry ice until it's not going anywhere and until we have solid dry ice in there. And then if you put a thermometer on this, then it's minus 78. So that is pretty cool. That is a reaction that discussed that industry still doesn't like it. But in the lab, to do minus 78 is trivial. Might not be sufficient for adding an alkyl lithium compound to an acid chloride because it's still not cold enough. You need to make it as cold as possible to have the reaction differences between the acid chloride and the ketone you're forming. So how do you make minus 100? Liquid nitrogen is a good idea, but liquid nitrogen, if you would immerse your flask into liquid nitrogen, you would be at minus 196, and you would probably your flask would break and everything. So you need to put the liquid nitrogen into something. Sorry?
Dewar glass.
In a dewar glass, but still, you still don't want to put your flask into the liquid nitrogen because then you're having minus 196. You need like we do with acetone, you need also a solvent. But you need a solvent which is not solidifying at minus 100. So what has a very low melting point? What type of solvents? Alkanes. So typically you take something like pentane or hexane. So if you want to do minus 100 degrees, very often you use, I'll put it up here, so minus 100 degrees, so as I say, minus 78, trivial. Dry ice, acetone. We all know this. If you go at 0 degrees, trivial, right? Normal ice. If you do minus 20 degrees, still pretty trivial. It's ice and something like sodium chloride. We make an ice method. Minus 78, Already a little bit more sophisticated, but dry ice is relatively available easy. Minus 100. This is typically pentane, liquid nitrogen. And you might say this is still easy because I have the liquid nitrogen tank outside. You guys have probably here, you must have a liquid nitrogen tank somewhere outside. And so, okay, then I just take a beaker. You don't take a Dewar glass because this might break at minus 100. You take a plastic, big plastic bin or so, and then you do it there. There is an element of danger in here, very, very severe danger. And that is especially, let's say, you come in the morning, you get in one of these Dewar bottles, you get your liquid nitrogen. And then on the afternoon, you decide, I'm now doing a reaction at minus 100 degrees. And now I take this from my liquid nitrogen bottle and I pour it into my pentane vase. So the question is, do I still have liquid nitrogen in that bottle, which you have gotten in the morning from the big nitrogen tank, and that was probably all liquid nitrogen. The point is you don't have it any longer because during the day you start exchanging with air. And so you have a significant amount of liquid oxygen in there. And now if you mix liquid oxygen with pentane, you have an extremely explosive mixture because pentane, of course, is flammable. And now you have an incredible, because it's liquid, you have an incredible high concentration of oxygen. And so you really, if this sees some spark or so, it will ignite. And so first of all, if you ever should do it, because there's no way, you always need to go fresh to the big nitrogen tank and get it, because you don't want to take a 1 day old the one from your normal bottle. But in general, it is hazardous, and so that is in general we try to and we should avoid such low temperatures, right? And so again, flow chemistry might be able to be a way around this, because again, the short reaction times might make it possible that here you have the acid chloride and you just mix, you make the phenyl lithium, then you bring the acid chloride, you bring it into this, and it will react immediately, but then you bring it out of your reaction system so that it doesn't have time to do a second reaction with a little bit less reactive compound. And so again, this is possible to do this in a good way. Okay, so then photo flow reactions. I see again we are running to the tea break. Let me do this here. So photo flow reactions are, of course, that is one of the best ways to do photochemistry. And we did here, it's an example from our lab, we did chemistry with the diazo compound. And so with the diazo compound, there is this danger of developing gas. And so we were also wondering, and we were very careful in the beginning, because there was also, when we did it, there was very little reported in the literature how to handle the gas which is being developed. And so what we have here, and you have essentially an oil flow apparatus, you have something like a back pressure regulator. And so when there's too much, when the pressure gets too high, it will reduce the flow intake of your compounds. And so this is here what we had. We had again 2 feeds. It's only shown here as one. We had the diazo compound, and we mix this, or in fact, because we do it on a photoreaction, only under light these diazo compounds decompose. So we have the diazo compounds, we had alkenes, or again furanes, you know that we like these, and we feed it into our flow reactor, which we can irradiate, and we could do the cyclopropenations. And you can see we could measure this. The pressure builds up, but we were able to keep it in a range which was okay for this photoreactor. And so this way we could, again, very short exposure times. Usually when we did these reactions, it was also on some hours could do this type of reactions. And the last example I would like to show you, because also I learned quite a bit of how especially industry is evaluating these type of compounds. We had developed 4 years ago an iodoamination, photochemical iodoamination. And it's very attractive because it's so easy to do. You take N-iodostoquinimide, this is this component. You take a protected amine, which has only one NH available, so we can take this N-methyltosylamine, and we take an alkene. And under irradiation, the iodine the N-iodostoquinimide gets reduced by the amine, so you have an electron transfer. You're making these N-centered radicals, and the N-centered radicals can add to an alkene, and then the residing radical can start a chain reaction and abstract an iodine from the NIS and make the final compounds. And so we thought we had this, and this is a really great reaction. Again, works very broadly with all types of alkenes. And so we thought we should demonstrate scale-up. And the way we wanted to demonstrate scale-up, obviously, was flow. And so we did this chemistry in flow, and in a almost trivial way, we took the three components, and we thought it's ideal because you don't need a catalyst or anything, and so we just pumped this through a photoreactor. I showed this, the low budget photoreactor, I showed it to you right away. We're forming the iodoamine here, and then we thought, why don't we add a second flow step to show something in addition? And so we then pumped the product through a tube which has potassium carbonate in there, and this will deprotonate the amine, and then in a nucleophilic substitution, you are forming aziridines. And so we thought that's pretty cool. This might be a fantastic demonstration for flow, and so easy because, again, no catalyst, you just shine light on this. And so here's how we did this. It's a photo which is a little bit misleading because we have two syringe pumps here, but in this case we only need one because we can mix it all. Without light, nothing happens. And so we mix it. You see here is again such a mixture. If you go from 2 feeds to mix things properly, but we only go from 1 feed here. So we mix this, and then here's our LED setup. We can cool the LED setup from the inside. You see this block here where we can put water or cooling liquid through this so we can keep it cool. And then we have, so the light goes into this tube here. And then you see what we have done. You cannot see so well. Maybe you can see it a little bit better here. We just take Teflon coil. Teflon coil is great for photochemistry because it's transparent. We just do Teflon coil and wrap it around that photo lamp. So very small, very easy way to do this. And of course, the idea is that you increase the surface area, right? And so we did this, and the reaction works great. And then here's the second step, right? This is even easier. So our photoreaction comes in here, and then you see we just have a tube which has potassium carbonate in here, and we just pump this through, and we have done this at 60 degrees in a water bath, so we have just put it there. And it worked very, very nicely, and so we were very, very happy with this. And then what you typically do is you check. After a time, you check always the yield, and so we let this run for a total of 4.5 hours, and we checked every 30 minutes. We took like a sample, and we saw, oh yes, the yield is high, and then the red samples, we actually isolated the product to compare in situ formation NMR yields with isolated ones. And so also we were very happy about this, and so we could produce very high yield, 3.04 grams per hour, and we could do this. But we had done this batch reaction before. We had done it in batch, and the one reviewer had read our paper very carefully, and he said, we all know that you can do scale up and flow, but your batch reactions seem to work in a similar way, and in the batch reaction, the scale up, we only made 2 grams. And so the reviewer said, so where is the advantage of flow? You should think more careful about if there's really an advantage. And I think he had a very good point. And the other thing is, we were very happy that this would run so constant over time without decrease in yield. And so in our paper, our title was a robust photoiodoamination. And the reviewer comes and says, you guys know this does not qualify for robust. Because yeah, we know this is any flow reaction in this case is robust because you're just over a longer time you're doing the same reaction. Why should this be robust? And he said, and we checked and we saw that many people used the robust in the way we did it, but this person was probably from industry and he said, robust means that you are not sensitive against certain influence of parameters. And so I show this to you then what we did in a moment. So we repeated the reaction in batch on a larger scale this time. So the one thing we saw is that the yield breaks down, and I think we know why that is. Because if you irradiate, especially when you have iodine or iodinated compounds over a time, you start, the reaction becomes dark. And then it becomes dark, and you could also see this in the UV spectrum. This is the initial reaction solution, but if you irradiate this for a time, then we build up and probably iodine and things like this. So the reaction becomes dark, and so that might explain why the efficiency in the batch is not as good, because you're forming colored compounds which you're not getting out like you would do it in flow, and so you suddenly start penetrating, your light penetration might not be as effective again. So a very simple consideration. We were very grateful to the reviewer that he pointed out that we need to make a better case why the flow is really helping us. And then when it comes to robustness, there is something which has become popularized by Frank Glorious, again, who's doing a lot of photochemistry, as the robustness scan. With robustness, it is really meant that how sensitive is your reaction setup against outside parameters or so. So it is. And then you typically have these robustness diagrams where here in white, this is like your standard conditions and there's no deviation of yield. So that's your benchmark, right? That's 0%. And then under certain reactions, the yield might actually even increase under certain conditions. But very often, if you have certain other conditions, the yield might go down. And so we tested this. And so one impurity of this type of reaction could be is that your NIS might have NHS present as a contamination. So here in this case, we added 10 more % NHS, and then you see we start here and the yield didn't change, right? And then we used undistilled styrene. Very often when you do alkene functionalizations and in a radical type regime, photocatalysis, you need to be aware that styrene very often is, when you buy it, has radical inhibitors in there because they want to prevent polymerization. So normally we always distill our styrene because we want to be sure, because we want to do a radical reaction, we want to be sure that there's no inhibitor in there which presents it. But in this case, you see, we took the undistilled styrene and saw if our chemistry is still working, and yes, it does. A typical contamination might be water. So we added some water and saw, is it doing anything? We changed the light wavelengths. We did the irradiation at 530 nanometers, and we saw that if you go to blue light, a little bit more energy intensive, we talked about this, you might form easier iodine. And so indeed here was the only type where we saw that the reaction yield went down a little bit. We recycled the solvent. And we saw that when we do the solvent recycling, the reaction still works well. We degassed the solution rather than running it on oxygen like we did originally. And again, it had a little effect, had actually a little bit of a positive effect, but so small that we decided that running the protocol under air, and especially when you do it in flow, to be sure that everything is degassed might be a little bit more difficult. Okay, so just a few ideas on flow. Tea break? I've talked again too long, right? God, it's so bad with me. You will hate me. Okay, that's okay. So that's the last day. I go home tonight. So, okay, so let's have a small tea break, and then I promise you we will just have a small discussion about an industrial and an academic synthesis of a very important compound, which cost our government 50 million euros a few years ago. Okay.